thank you for not only coming, but also staying for the very last presentation on smooth single-shot entropies and the resource theory of nonuniformity.
Not sure why this isn't working.
Do you have a plug-in?
Yeah.
Does the computer?
There's an on switch as well on the clicker.
There's an on switch on the clicker.
Oh my god.
Many of us know Sziller's engine. It's a device for turning information into work. Suppose you have one bit of information. You have a box that contains a particle. You can think of it as an ideal gas. You know that the particle is in one side of the box. So you can slide a partition into the box, tie to the partition a rope, tie to the rope a weight, couple the gas to some temperature T heat bath, and let the gas expand. It pushes the partition, lifting the weight. At the end of this process, the particle could be anywhere in the box. You traded information about the particle's location for work. This story illustrates why we might want to use quantum information theory tools to analyze thermodynamics. We're also going to want to use quantum mechanics. Technologies are getting smaller and smaller. People are thinking about nanoscale engines. People are studying molecular motors in biological systems. Even classical computation, not to mention quantum computation, involves the transformation of some free energy into a computation and waste heat. So all these applications involve the interplay of energy and information on a small scale. That's why we're using quantum information to analyze thermodynamics.
So I'm a little bit confused, sorry. I understand you want to use information theory to understand thermodynamics. That's great. But why quantum? For a refrigerator or a Sziller engine that is this big, right?
Well, so you're talking about a refrigerator that's this big?
Yeah, that's right, like this guy.
Yeah, actually, Sandra Popescu and Noah Linden wrote a few papers about the smallest possible refrigerator. So they were thinking about a refrigerator that consists of a feature, just one 3-level system. That's definitely quantum. A lot of the work that we did does map right into classical dynamics, but we could extend to the quantum realm.
University residents are getting smaller.
Yes. More motivation. Well, we are going to be talking about one copy of a quantum system. The thermodynamic systems we're talking about are small. Also, the ones that we're focusing on have trivial Hamiltonians. Why study trivial Hamiltonian systems? Thermodynamics is complicated. It involves all sorts of parameters. We're starting with this small, simple system so that we can get an intuition here and then apply our understanding to the more general thermodynamic picture. We're going to focus on resource theories, particularly the resource theory of nonuniformity, which is the thermodynamics of those simple systems. The tools that we're going to use to mathematically describe the resource theory of nonuniformity are entropies and Lorenz curves. Our main results are single-shot inequalities, conditions under which some set of operations can and cannot transform some quantum state into another state. We will show that we recovered and generalized a known optimal asymptotic transition rate. I'll explain what on earth that means. I won't have a lot of time to talk about information measures or limiting Lorenz curves, but feel free to ask about those during the Q&A. A resource theory is a simple model that highlights one facet of quantum information. Perhaps the most famous example is the resource theory of pure bipartite entanglement, and part of this audience has contributed a fair amount to that. Also, thermodynamics has been modeled by a resource theory, the resource theory of athermality. That's what we'll generalize to after studying our simple case. Why talk about resource theories? Well, suppose that you're an experimenter in a lab. You create and manipulate quantum systems. Probably some systems are so easy for you to create just because you have the skills and the resources that you can think of doing it for free. These states we call free states. Any states that you cannot create for free on your own are scarce. They're valuable. You can't create them yourself, but maybe someone from the lab down the hall can transform by free operations, again, whatever operations are easy for you to do, any state that you have in your possession. In the resource theory of non-uniformity, the free states are uniform states. Here's what they look like. In the resource theory of non-uniformity, in order to specify a state, all you have to do is specify the dimension of the space on which the state is defined and the spectrum of the state. Suppose that you have a state defined on this space. Suppose that its spectrum looks like this. This is the maximally mixed or uniform state. That's free. An agent in the resource theory of non-uniformity can create as many copies of that on whatever dimensional spaces as he or she wants. Now, any state that does not have that spectrum has some non-uniformity, some purity. These states are valuable and cannot be created for free. The free operations in this resource theory we call noisy operations. They tend to decrease information contents. Each noisy operation consists of up to 3 steps: tensoring on a uniform state, transforming by any unitary, and partially tracing out a subsystem. When we study resource theories, we study transformations. How many copies of this state can I transform into how many copies of that state? How efficient or costly are transformations? We do this in order to better understand the resources and the free operations. I use that symbol to communicate that noisy operations can transform some quantum state rho into some state sigma. So when you see that no, think, yes, noisy operations can implement the transformation.
So how do I think of noisy operation? I mean, mathematically or formally?
Yeah. It has this form mathematically. Let's suppose that you start off with some state rho, and we're going to call our noisy operation E. The E of rho has this form. First I'll write it, and then I'll explain it. First you take your rho, tensor on any maximally mixed state you want. Then you perform a unitary that transforms the whole thing. Then you can partially trace out a subsystem. You want for the dimension on which this is defined, and the dimension on which, well, you want all the dimensions to match up in the end. Basically, the dimension of the space you begin with has to be the dimension of the space that you end with. That's the constraint on this.
What's the unitary? How do you know what that is? Anything you want it to be?
Well, in this case, we are dealing with systems that can be talked about just in terms, in classical terms. In this case, we're talking about stochastic matrices, particularly doubly stochastic matrices.
So unitary is some stochastic matrix. I don't know.
Sorry, would you mind rephrasing your question?
Well, just you say you put unitaries there, but you don't tell me. I mean, is that
Oh, sure.
what is the unitary I choose? Anything I want it to be, or
Yes.
is it?
In this theory, in this resource theory, any unitary that you want is free.
Okay.
And if you move to the thermodynamic theory, then you have a restriction on your unitaries.
Okay.
For classical partition functions, we know this notion of doubly stochastic matrices, where you would see that your initial probability distribution is mapped into one that is obtained by a sum of a mixture of permutations of the original one. Is that possible in this formalism? Is that included here?
What you're saying is every noisy operation a sum of permutation matrices?
No. There is a notion for classical probability distributions of what a noisy operation would be. And it's expressed in terms of a doubly stochastic matrix, which can be understood as a sum, a probabilistic sum of permutation. So this looks like the non-diagonal part, an extension to quantum mechanics of that. And I'm asking, can you confirm that this is an extension? That this one can reproduce the classical case?
Actually, we can. So suppose that we start up with this rho. We can use any unitary. We're going to also diagonalize it. If this is diagonal, let's say these are diagonal on the same basis, this whole thing becomes classical, and you can just represent it as a probability problem.
Right. And my question is, can this represent a probabilistic sum of permutations on the diagonal part of this matrix?
I don't know off the top of my head,
Okay.
but
No, that's fine.
the permutation matrices and that sort of thing are exactly what we're reducing to when we talk about going from the quantum to the classical here. Again, we use two tools to represent the resource theory of non-uniformity mathematically. One of them is entropies, actually a really complicated species of entropy. I'll introduce it in 3 steps. First, the entropies that we've known about for decades. You probably recognize the Gibbs entropy from statistical mechanics. Consider some thermodynamic system that consists of a lot of particles. It occupies some macro state represented by rho. The Gibbs entropy of rho quantifies the uncertainty about which microstate the system occupies. The von Neumann entropy looks similar. Now think about a quantum system that occupies a quantum state, represented by the density operator rho. Suppose that you measure some observable of the state of the system that commutes with rho. The uncertainty about the measurement's outcome is given by the von Neumann entropy. The Shannon entropy is the classical analog of the von Neumann entropy. It's usually introduced before the von Neumann entropy, but for our purposes, the von Neumann entropy of a state rho is the Shannon entropy of the spectrum. These entropies have operational significances in what we call the asymptotic regime. Here's what that means. Suppose that you have some number n of copies of quantum states. In the limit as n approaches infinity, this context becomes the asymptotic regime. But if you have many, many copies of a state, then you can perform operations like data compression on this set of states. The von Neumann and Shannon entropies give the maximal rates of efficiencies with which you can do these operations. But usually, we don't have n approaches infinity copies of a state. But that's why we talk about the single-shot entropies, the max and min entropies. They get their names from a generalization of this relationship, and their definitions look funny, so we'd better parse them. The max entropy is defined in terms of the dimension of the support of rho, which is the number of non-zero eigenvalues of rho. Min entropy depends on P max, which is the greatest eigenvalue of rho. We found that the max and min entropy quantify nonuniformity, or distance from this maximally mixed state. To give you just a flavor as to why this might be the case, I'll ask you to think about the pure state. It's as far as you can get from the uniform state, and its greatest eigenvalue is 1, the greatest possible eigenvalue of any quantum state. That greatest eigenvalue, 1, appears in the min entropy. So the min entropy tells us something about the pure states being very far from the uniform distribution. That's one reason to think why these single-shot entropies tell us about non-uniformity. If you have just 1 copy of the state, or 1 copy of a classical random variable, then you can also perform operations like data compression. And in this context, it's the single-shot entropies that give you the rates of maximal efficiency. These, the smooth single-shot entropies, are the entropies that we're going to use. They were invented by Renato Renner at ETH not long ago, and they're really complicated. So let's take them apart. The smoothness is a parameter epsilon, usually close to 0. Let's look at how to calculate the smooth max entropy of the state rho. We start with rho, and find all the states rho tilde that are epsilon close to rho. We choose a distance measure, a measure of the distance between quantum states, like the trace distance. We find all the states rho tilde whose distances from rho are less than or equal to epsilon. We calculate the max entropy of each rho tilde. The minimum max entropy is the smooth max entropy of rho. We calculate the smooth min entropy of rho similarly.
So I'm sorry, how would you define the distance again?
The distance?
Yeah, what is it again?
It depends on what you want to use. There are a few choices. A popular one is the trace distance. I can write the form of the trace distance. distance measure that we used is called the purified distance, and it's defined in terms of the fidelity.
And this definition doesn't really matter, doesn't depend much on the definition of distance, the definitions of maximally when h equals. It's independent of how you define it, right?
Well, you can sort of choose your D, and then one useful property that we use, because some of the literature involves the trace distance, some involves the purified distance, but the purified distance upper bounds the trace distance. So if someone proves some property of these entropies that we want to use, and they use the trace distance, but we use the purified distance, we just make sure that the bounds work out, things like that.
But it seems to me actually the opposite. It seems to me in general that these definitions are contingent on what you use for your distance measure. Is that correct or not correct?
Yeah.
Like if I use one distance measure, you use another, it's not clear to me we will agree on h max and h min.
Yeah.
That's correct, is it?
Yeah, the distance measure is something that you choose.
Yeah. Okay.
But if different people use different distance measures, then the relationships between the distance measures can enable them to communicate about their results that involve the entropies.
Sure.
Anyone else? The second mathematical tool that we're going to use to analyze the nonuniformity theory is the Lorenz curve. This is also decades old. It actually came up first in economics. It's a means of visualizing a probability distribution, which the spectrum of a quantum state is. Now, here's how to create a Lorenz curve. Start with the spectrum of your state. Order it from greatest eigenvalue to least eigenvalue. Each of the eigenvalues corresponds to one of these black dots, except for the origin. Now, except for the origin, the first black dot has a y-coordinate that is the greatest eigenvalue of rho. If you add the second greatest eigenvalue, you get the y-coordinate of the next point. As you keep adding eigenvalues, you move farther and farther along the curve. That's mostly what this piece of K means. Here are a few other Lorenz curves. This is of the pure state. Notice that it slopes upward very sharply and has a very long horizontal piece. This is the Lorenz curve for the valueless state. It's the lowest possible Lorenz curve. Because every Lorenz curve is concave, it cannot bow toward the x-axis, and it extends from 0, 0 to 1, 1. We'll see shortly why these particular states should have these Lorenz curves. We found that the Lorenz curves have interesting anatomies, and the single-shot entropies quantify those anatomies. This first flat bit of the curve I call the on-ramp, and its slope is given by the min entropy. That final flat part, the horizontal part, I call the tail. Its length is quantified by the max entropy. And now that we have these Lorenz curves, let's see how to use them in the nonuniformity theory. If and only if the Lorenz curve for rho is everywhere above or on the Lorenz curve for sigma, noisy operations can transform rho into sigma. So here we see a rho curve that is everywhere above or on the sigma curve, so the transformation can happen. Here we see a rho curve that dips below the sigma curve, so the transformation cannot happen. Now that we have these two tools, let's see what we're going to use them to solve. I'll explain shortly why we want to answer these questions. Suppose you're an agent in the resource theory of nonuniformity. You have some state rho. You're thinking about a state sigma. You'd like to create it, but you don't have to create it exactly. Some sigma tilde that is epsilon close to sigma is good enough. So under what condition on rho and sigma can noisy operations transform rho into some sigma tilde? And under what condition can noisy operations not transform rho into any sigma tilde? Here are the answers. I call them a go inequality and a no-go inequality. If rho and sigma satisfy the go inequality, noisy operations can transform rho into some sigma tilde. If rho and sigma satisfy the no-go inequality, noisy operations cannot transform rho into any sigma tilde. Let's look at their forms. On each side of each inequality, we see a log d minus a smooth single-shot entropy. The d is the dimension of the space on which the state is defined. Notice that all of these entropies are smooth. The epsilons will become important for a reason we'll see later. Log d minus a max entropy is basically the amount of non-uniformity that noisy operations can extract from a state, sort of the distillation rate of nonuniformity. Log D minus H min is basically the amount of nonuniformity that you need to create that state. The nonuniformity cost of creation, cost of formation. Basically, the inequality is saying if rho has if you can extract from rho at least as much nonuniformity as you need to create some sigma tilde, noisy operations can make the transformation. And if you cannot extract from rho at least as much nonuniformity as you need to create some sigma tilde, you cannot make the transformation. There are a couple of ways to prove these inequalities. I'll discuss the strategy that I described in my essay. We discovered last week what seems to be a more geometric and more intuitive proof. But the proof that I'm going to talk about has two steps. The first part is more geometric, the second is more algebraic. Step one involves this. The single-shot entropies quantify the Lorenz curves. The Lorenz curves tell us whether or not rho can turn into sigma. So we formed inequalities that involve the single-shot entropies and tell us whether rho can turn into sigma. But remember, we needed smooth single-shot inequalities. And we wanted to talk about sigma tilde, not sigma. So to get those epsilons in the inequalities, we used basically just algebra, logic, and definitions. Not super informative. So I'll illustrate step one, but not step two. The rho cannot transform into sigma if the Lorenz curve for rho ever dips below the Lorenz curve for sigma. In particular, if the on-ramp for rho is below the on-ramp for sigma, which means the slope of the rho on-ramp is less than the slope of the sigma on-ramp. Remember, we have expressions for these slopes in terms of the min-entropy. If we simplify this inequality, we get our non-smooth, no-go inequality. To get the epsilons in here, again, we used logic, algebra, and definitions. Not super illuminative, but it works.
Is there some intuitive understanding of this no-go?
Yeah. We can think of this as saying, more or less, you can't get enough non-uniformity out of rho in order to create sigma, because there's some maximum amount of non-uniformity you can extract using noisy operations, and there's some amount that you need in order to create sigma. Basically, that's what the inequality is saying. Now, why did we ask these questions? Hugh Hordetsky and Jonathan Oppenheim had studied the resource theory of non-uniformity in the asymptotic regime. We wanted to generalize their results to the single-shot regime and to inexact inequalities, where we don't have to create sigma exactly. So they came up with an optimal asymptotic transition rate. Here's what that means. Say you have a number of copies of rho, and you're creating copies of sigma. The maximum number of copies of sigma that you can create per copy of rho is the optimal transition rates. In the asymptotic limit, this quantity becomes the optimal asymptotic transition rate. That is what the Hordetsky and Oppenheim calculated. That's what we recovered from our single-shot inequalities and generalized. Notice the form of this formula. I involves a log D minus an entropy. Look familiar? That's because in the asymptotic limits, the smooth single-shot entropies converge to the von Neumann entropy. The non-smooth epsilon-free single-shot entropies do not necessarily converge to the von Neumann entropy. That's why we needed those complicated epsilons. This I, the Hordetsky and Oppenheim call the unique measure of information. We also studied it. In the asymptotic regime, it does indeed have a unique relationship with information measures for some physically intuitive meaning of information measure. So we studied this and also proposed some single-shot analogs. Don't have time to say much about limiting Lorenz curves, so ignore the math for now. The big idea is, if you have several copies of a state rho, then this whole thing is a state. You can draw its Lorenz curve. We expect its on-ramp slope and its tail length to be quantified again by entropy. They are quantified by entropy. In this case, the von Neumann entropy. So we obtain expressions for that quantification. And we also, what I think is really cool, is found that in the asymptotic limit, it doesn't really matter what row you start with. As you obtain more and more and more copies of rho, then your Lorenz curve approaches one of two canonical limiting curves. Feel free to ask more during the Q&A. We've seen that quantum information offers useful tools for analyzing thermodynamics. The tools that we use are the resource theory framework and informational entropies. We focused on the resource theory of nonuniformity, which models simple thermodynamic systems that have trivial Hamiltonians. The tools that we used are the Lorenz curve and the entropies, the smooth single-shot entropies. Our main results are single-shot inequalities, conditions under which noisy operations can and cannot transform some state rho into some sigma tilde. We recovered and generalized a known optimal asymptotic transition rate. We studied and defined information measures, and we quantified limiting Lorenz curves. All in the service, hopefully, of better understanding thermodynamics, and maybe down the road contributing to applications. So now that the essay has been turned in, we are applying our understanding of the nonuniformity theory to the more general thermodynamic resource theory. Thank you for your attention.
Okay. Well, thank you very much. That was fun. So let's see. Can you tell me something about the physics here? What do you have in mind? I mean, I know you mentioned thermodynamics, but you were not sort of constructing a situation where I could imagine this being applied. Can you make some illuminating comments about this? Let's say, for example, these inequalities. Do they have a thermodynamic meaning? What do you have in mind? Is this something about the second law?
Second laws do come up a lot in this resource theory of athermality literature. So in order to understand that, again, we're simplifying those systems. So in the literature that concerns the thermodynamic resource theory, people talk about, suppose that you have a number of Szilard engines, each contains one particle. That's their physical system. So that's how it would look, since you're asking for a physical intuition. So we might start with something like that, and then say, we're going to look at these systems, but in the case in which they have zero Hamiltonians. So they do not evolve by themselves in time. Those are the systems that we're looking at.
So suppose you turn on, I don't know, a non-zero Hamiltonian. How would this change? How difficult it is to generalize to very simple Hamiltonian, but something that is not zero, so you can evolve in time. Because after all, when you think about second law or something, you want some type of time evolution.
The resource theory, or a resource theory in general, involves three key aspects that sort of define each other: the free states, the scarce state, or the free states, the scarce states, and the free operations. So we saw in the nonuniformity theory, the free states are the uniform states. In the athermality theory, the free states are Gibbs states. And you know, the Gibbs state looks like where the z is the trace of this. So if you take this h equal to 0, then this becomes 1. Z becomes the dimension of the states, and you get that your spectrum for the uniform state.
Yeah.
So any state that does not look like this is a scarce state. For example, a pure state, the most valuable pure state is the pure state in which all the probability is on the highest energy. And also free operations, they become just the operations, just the unitaries that commute with the Hamiltonian, because they have to conserve energy in accordance with the first law. So those are some of the differences.
So should I think of this as the infinite temperature limit?
We were thinking about that.
Yeah.
So in some ways that works. For instance, if we're looking at beta here, then taking temperature at infinity seems to reduce this to the simple quantity that we want. Problem with that could be here. Because if we say that you take the athermality theory and just temperature approaches infinity, then you have no reason to believe that all the unitaries will come to commute with the Hamiltonian, and so all the unitaries will come to be free in the nonuniformity theory. We need for our limit to enable all the unitaries to become free in the nonuniformity theory. So it seems like perhaps infinite temperature doesn't do quite all of the job that we need.
Rob?
Yeah, I thought this was a very nice presentation. I'm still want to ask elementary questions. So you start off with uniform states, which would have this straight line Lorenz curve, right? Now, am I right in thinking noisy operations are going to push this to something concave?
Noisy operations tend to lower the Lorenz curve toward the uniform distributions.
Okay, that's what I thought, but this is where I got confused, because I thought if you start out with those free things, I thought you were asking what can you do if you get something for free and turn it into something that wouldn't be for free. So I'm sort of missing the flow of reasoning in a broad sense, I guess. Because I would see how noisy stuff could turn something concave into flat, but I thought you were like if you get this for free, that's what you start with, and then you're doing stuff to it to make it less than free. Is that right? I'm puzzled here.
So
go ahead.
we think of an agent who's given some state rho, not some arbitrary distribution for the spectrum. Again, it's someone from the lab down the hall who gives the agent this, so we do not consider this a free state. It's just a state that the agent has been given by someone who could make it. And so it could be valuable. So we could have an arbitrary curve like that. That's clearly a valuable curve because it's not straight. So the agent can perform noisy operations on it, and while performing noisy operations, the agent causes this curve to decrease towards the maximally mixed curve. Now, if the agent wants to create a state sigma that is represented by a curve that is lower, that is more like the maximally mixed curve than the rho curve is, then noisy operations can make the transformation. The agent can transform rho into sigma. So by tensoring on the uniform state and doing unitary, tracing out parts of states, the agent lowers the curve.
Okay, so what's the agent getting out of this? I mean, because you can get the sigma stuff for free. So why do something to a state to get a state you could get for free? This is, I guess, what I'm missing. What's the incentive?
One of the motivations for making this transformation can be seen in the athermality theory. So we saw in thermodynamics, you might have information and want to turn it into work. Here we see that how far the Lorenz curve, or how different the Lorenz curve is from the uniform state, is a measure of the amount of information in your state rho. So as you perform noisy operations on your state rho, you might be transforming the information in rho into work, like lifting the weight. So that's why you might want to lower the curve.
Okay, so do we know that for sure? If I take a rho that's curved this way and I perform noisy things on it to get it to be more and more uniform, like more and more straight line, am I guaranteed I can always turn that into work? Or is that not yet known?
Well, if you look at Ziller's engine, Landauer's principle, according to those stories, it should be possible. Also, in the resource theory framework in general, these quantities are what's studied, what transformations can and can't happen, and the rates of transformations. For example, in entanglement theory, that's what's studied. The von Neumann entropy is one of these gold standards for transformation rates. So in the non-uniformity theory, we want to do the analog of what was done in the entanglement theory in order to understand the non-uniformity theory as well as we understand the entanglement theory.
Okay, so the answer, I would interpret that to mean partly no one, I guess. Is that, I mean, you're saying you expect it could be done, but that's not the same thing as saying to me that we know it could be done. Am I right or am I not right?
Well, what I'm saying is that there are two motivations. One is just this is what we have to do in order to analyze a resource theory thoroughly. And two is in this particular resource theory, there's the physical motivation of being able to do work. In the entanglement theory, the analog would be if you use up some of your entanglement, so doing the analog of lowering the Lorenz curve, you might be simulating a quantum channel. So in these cases, we're using the resource, using information, using entanglement, in order to do something useful, like lift a weight or simulate a quantum channel.
Okay. All right.
So what would the inequalities mean in the entanglement theory?
The analog would be basically what I said about non-uniform. I made statements about non-uniformity. Stick in place of non-uniformity, entanglement. So if, and instead of noisy operations, substitute local operations and classical communication.
Yeah. So what would then how would I read these inequalities or?
Yeah. Actually, basically, if LOCC, local operations and classical communication, can extract from rho, if the rate of distillation of entanglement from rho is at least enough as the entanglement that you need to create sigma, so at least as great as the entanglement cost of formation of sigma, then the transformation can happen. And I'm omitting the sigma tildes because they just make things complicated. Basically saying the reverse would be the no-go inequality.
There's another question I had is, what does it mean? Okay, inequalities I can sort of intuitively understand, second law and so forth. How about the first law? That's an equality. And what does it mean when h is equal to 0?
I wrote before here, this is a restriction on the free operations in the aformality theory. So the first law I see as an assumption in our aformality resource theory.
I was going to ask about entanglement, but I want to follow that up a bit with a previous question about it. So you talked a little bit about what would happen with entanglement here. There's this other quantity called quantum discord that you have better than classical correlations, but you're not entangled. Or would you be able to say something about that using this?
If I knew more about quantum discord, possibly.
All right.
I've heard the term around, but I'm not very familiar with it.
That's okay. Fair enough.
Any other questions?
Yes. So I would like, this is more about my ignorance of your talk, but maybe you can clarify this. So I'm familiar with the entanglement part of it, and there the inequalities that you have are majoritization. Are these Lorenz curve completely equivalent to that?
Almost.
Almost.
They're a generalization.
I mean, before you put the epsilons.
Oh, by the way, since you said something about energy, just when I wrote this, I was assuming since these two commute with each other, that implies that this unitary conserves and Hamiltonian conserves energy. I just should have said that at the end. So suppose you have a rho, a sigma, and they're defined on the same space. So they're the same size. Then what we need in order to solve the problem is the majorization relationship. But if they are different sizes, then, as we can see here, remember each of these black dots represents an eigenvalue. So the rho curve has fewer eigenvalues than the sigma curve. So we can't make that majorization relation comparison. But the Lorenz curve enables us to make a more general comparison. And just if the space sizes are the same, then our Lorenz majorization reduces to majorization.
Okay, very clear. So the difference is that in entanglement theory, you can put a product state, and that would correspond to adding a pure ancillary, which you cannot perform here.
We cannot tensor on a pure state, so we cannot
Right.
embed it.
That's why you did it. Okay.
But so this is the geometric visualization of the comparison. The algebraic visualization, or the algebraic analog, is so if you have two states of different sizes, then you tensor on a maximally mixed state to each of the states, so that the products have the same sizes, and then you can do the majorization relation. Because tensoring on a maximally mixed state preserves the Lorenz curve. That's why the Lorenz curve is so useful in the resource theory of nonuniformity.
Okay, are we done here? Any other questions? Okay, let's
Great.
go again.